Okay, so that's close enough. This is problem 3. Problem 3 is quite similar to problem 1 because it's a stress problem. You're just interested in finding the stresses. In this case, you're given a point. You're given the shear axial force and moment at this point. So all that is calculated for you. Yeah, it's very similar to problem 1. So I'm going to go speeding through this quite quickly, and I'm going to spend most of my time talking about Mohr's circle. Recall that for bending stress, let me see, I lost my sheet. Please. My over I, this equation here. This y refers to the distance from the neutral axis to the point you're interested in. This y bar here represents the neutral axis, and you're interested in the distance from here to here. And if you want that, I'll just give that to you because it's very easy to calculate. It's just 150, the dimension of this, minus y bar. So that is the y you should use here. Your tau, I went over this earlier. Recall for a, I'm going to just draw a T-beam really quick like this. You want to use the largest stress that develops here. And for that, shear acts this way. So you want to use this area. And you want to use the y bar through the center of here. Now this y bar that I drew here, this y bar is not the y bar that's given to you. So I will call this y prime. The y prime, this is y bar. Y prime is this distance. And that will be your q. Q is this area times this distance. Yeah, that is pretty much all of it. Okay, so the next part of this problem is Mohr's circle. I don't know about you. I never really did like Mohr's circle, but it is actually important, especially if you're going into any sort of geotechnical stuff. You have Mohr's circle everywhere there. Foundation mechanics, soil mechanics. Yeah, Mohr's circle is important. That doesn't mean you have to like it. You just have to know that it's important. Okay, recall that you have, this is going to be general for Mohr's. It's going to be specific to this problem later, but for the basic stuff for Mohr is that when you, in a natural state, you have something that has sigma x, sigma y, and tau, and tau. I'll just leave it tau. I won't include the subscripts because I don't want you to get confused on your notation. I want you to notice here that we only have one. Okay, if you have this beam like this is deflecting. If you have this, it's pointed downward, right? It has loads like this. It's bending. You have forces that are acting in here, right? So you have axial forces. You only have axial forces in a single direction in this case. So pretend that I have a sneaky suspicion that I'm going to screw this up really badly. But pretend that this is you have a cross section like this, right? Pretend it's like this. So pretend that let's say that this is point A. This is a side view. Pretend that this is like this. So it's here. It's going into the page, this thing. Then your sigmas that you have here are all going to be sigma x. And you're not going to have any sigmas that are acting in the upward down direction. You're not going to have any of these sigmas. You're not going to have any sigma y's. You're only going to have sigma x. You still have tau. Tau is your shear stress. Tau is, recall that you have no torsion in this problem, so this goes to 0. Once you have this setup, you can draw this square here. So you have this square. I already said this is 0, so I'll just draw the shear. Now what does this represent? Recall that when you're drawing your Mohr's circle like this, you have the sigma x and sigma y, whichever one is larger, over here. We'll call this sigma x because it's, I should say sigma large equals sigma x all the way over here, and it acts downwards by tau. And yeah, when your tau is positive, you give this thing a negative slope. So you put your tau downwards like this. Now over here you have sigma small. Sigma small somewhere. Sigma small is just 0 because there is no sigma y. Sigma y is equal to 0. So you just put it on this axis and you go up by tau. And you draw this. And this is your plane that you're starting with. It has a center. The center is sigma x plus sigma y divided by 2. And it also has a radius. The radius, recall that the radius is just equal to tau max. And if you draw this, let's see how well I can draw a circle today. Yeah, okay, it's a crappy circle, but you get the picture. This is some angle theta. Theta p to be exact. Theta p is the distance, the angular distance from the plane to theta p. Now to find that theta, you're going to use the equations. All the equations you need for Mohr's circle are given to you in this problem. They're all given here. So use tan 2 theta p. The reason why this 2 exists, I'm not going to give you, I don't know if there's probably a more technical reason, but the 2 theta means that when you're on this graph, you rotate everything by 2 times the angle. When you're working with this little block, you only use the angle. So for example, let's say we had one block that was the principal axis and it was flat like this, and these were your principal stresses. If you rotate it by 90 degrees on here, 45, if you rotate it by theta equals, sorry, what am I doing? This is P min, P max. If you rotate it by this is rotating it this way to get here. You're going from here to here. Now, in our case, you can actually just use a handy little formula. Remember that that the maximum principal stresses and the maximum shear stresses are going to be at right angles to each other. So what does that mean? That means that you can just use theta p equals plus or minus, theta s equals plus or minus theta p plus or minus 45 degrees. And you're going to use whichever one is closer to you. So in our case, it's easier to go from here downwards. So our theta s equals theta p minus 45 degrees. It's going this way. So yeah, that is, oh shoot. I hope everything is being caught on the camera. But yes, that is your thing. That is how you get your theta s. Now, to calculate these forces directly, you don't actually need to graph all this right away. You can just use this. You can use these equations. Remember I said sigma y is equal to 0. Tau xy for, I said that the maximum stresses occur when the maximum stresses are when tau is 0. That does not mean that you use this as 0. This is saying that given your initial conditions, this is what your maximum will be. So for example, our initial conditions had some small tau. We have a tau from our problem. And you're going to plug that into here. You're going to plug the sigma x, which you got from part A, into here. And you're going to use that to find sigma min, sigma max. You're going to use the same stresses here. It's slightly different formula. You get tau max. And then you're going to graph this. When you graph it, do try to draw a 2-scale. That's the important thing. Yeah, and just some like advice, I guess. Like, Mohr circle actually does save you a lot of time on an exam, because it's a lot easier to see a problem visually. And if you know how to use it, if you look at it and you can solve it visually, not just visually, but like graphically, it's just a lot faster. You'll be able to identify your mistakes, assuming you know how to use it properly, very quickly. So it's a great exam tool, especially on like the FE, the engineering training exam. Its graphical tools are very useful. And exams too, and it's just something that's useful to use, useful to know. You don't have to like it, but it is useful. It's like vegetables. You don't have to like them, but you should eat them. Anyway, let us know if you have any questions or if you need more help.